In this video, we're going to take the examples that we had solved previously using the substitution method and applying the elimination method, also referred to as the addition method, to solve the same system of equations. This is just an alternative method for solving systems of linear equations. When you're solving these, it really doesn't matter whether you use the substitution method or the elimination method. They are equivalent, the same, you get the same answer. It's more based on preference. All right, looking at the steps of the elimination method. Step one, you're going to start out by multiplying one or both equations by a constant in order to eliminate one of the variables. And then step two, once you've eliminated either x or y, you can then add the two equations by combining like terms. And when you add, that's going to cancel out the x or the y, leaving you an equation of only one variable. So step three, and this step goes back to just the regular substitution method. Solve for the remaining variable, and then step four, substitute into either equation to solve for the other variable. So it's really steps one and two that are different from the substitution method. All right, let's take a look at this elimination method using the following example. We have seen this in a previous video. We used the substitution method. This time we're going to use the elimination method. All right, so we want to multiply one or both equations by a constant to eliminate one of the variables. It does not matter which variable that we are eliminating. But in order to eliminate the variable, when we add, we want the coefficients of that variable to be additive inverses. Additive inverses, that means when you add two numbers together, these two additive inverses together, you get a sum of 0. So an additive inverse will have the same number but opposite signs. So for example, if I were to eliminate the variable x, I need those coefficients to be the same number but opposite sign. The first coefficient, the coefficient in the first equation for x is 3, a positive 3. So that means I want the coefficient of x in the second equation to be a negative 3. Okay, right now it's just sitting at a negative 1. So I need to multiply that second equation by a number so that the coefficient of x becomes a negative 3. Negative 1 times 3 will give us a negative 3. So we're going to multiply that second equation by 3. So I'm rewriting the first equation, that doesn't change, and I'm multiplying the second equation by 3. Every term in that second equation is being multiplied by 3. So 3 times negative x is negative 3x. 3 times 2y is 6y. 3 times 9 is 27. So now step two, now that I have additive inverses for my x's, I'm going to add. And of course, 3x plus a negative 3x cancels out. That's what we want to happen so that we're reducing our problem down to just one variable. Y plus 6y is 7y, and 1 plus 27 is 28. Now divide both sides by 7. 28 divided by 7 is 4. So we have found that y is equal to 4. And now we're ready for step 4. Substitute 4 into either equation to solve for the other variable, solve for the x. So it doesn't matter which one that we substitute here. I'm just going to plug y equal 4 into the first equation because it's the first one. So 3x plus the y, and that's 4. So 3x plus 4 equals 1. And now solve for x by subtracting 4 from both sides. 1 minus 4 is negative 3. And then divide both sides by 3. Negative 3 divided by 3 is a negative 1. So we've found the x and the y. We'll write that as an ordered pair. Negative 1 comma 4. You can check from the previous video that that agrees with the solution that we found using the substitution method. Okay. We'll look at two more examples here, just to give us a good idea of that elimination method, how it works in some different cases. And these are all the same examples from the previous video. So you should know what the answer will be and kind of know what to expect when we get there. All right, solve the system of equations. We've got x plus 2y equal 3, 2x plus 4y equals 6. All right, we want to multiply one or both of the equations by a constant so that we get additive inverses for either the x or the y. Does not matter which one. All right, so looking at, again, the x's. Okay, I've got a coefficient of 1 for the first x in the first equation, and a coefficient of 2 for the x in the second equation. Now, if the coefficient is 2 in the second equation, I would want the coefficient of x in the first equation to be -2. So we would need to multiply that first equation by -2 in order to make that happen. So -2 times x is -2x. -2 times 2y is -4y. And -2 times 3 is 6. The second equation remains the same. So I'll copy that over. 2x plus 4y equals 6. That should be a -6 in the top. All right, so now we add, right? And that should eliminate our x's, right? -2x plus 2x is 0. But in this case, it's also canceling the y's. -4y plus 4y is 0. So we have 0 on the left-hand side since both of the x's and the y's canceled. And on the right-hand side, -6 plus 6 is 0. All right, remember when we were working this example using the substitution method, we had a true statement. We had gotten 6 equals 6 in the substitution method. In this case, it's 0 equals 0. Anytime you have the same number equal to each other, that gives you a true statement, right? Which means that there are infinitely many solutions. So in this case, to write a general formula for our solution, we said x can be anything, and we can write that as x or t or whatever variable that the direction may be asking us for. And then we solve one of the equations for y. We're writing y in terms of the x or in terms of the t. Right, and that was taking the first equation and solving for y. Subtract x from both sides. We'll redo this. But this should be the same steps as what we had seen previously. All right, divide both sides by 2. That's y equals 3 divided by 2 minus 1/2 x. And so our solution, our infinitely many solutions, the general form for that is x comma 3/2 minus 1/2 x. Okay. All right, and our last example we'll have the same approach because this was our no solution example. Again, we're multiplying one or both equations in order to get an additive inverse. And again, I've been picking on the x's. You could just as easily pick on the y's as far as eliminating them. I've got a 3x and a 6x. The 6x here in the second equation implies that I would want to get a -6x in the first equation. To get a -6x, I would need to multiply by a -2, right? Because -2 times 3 is -6. So -6x. -2 times -2y is a positive 4y. And -2 times 5 is -10. And then we copy that second equation. We didn't do anything to that one. Okay, so when we add, again, the same thing happened as the previous example. The -6x plus 6x cancels out, which is what we were wanting to. That's why we multiply by the -2. But also the 4y and the -4y also cancel. So we have 0 on the left-hand side. But now in this case, the right-hand side does not give us 0. -10 plus 2 is -8. Right? And this is our false statement. Right? When we have two different numbers equal to each other. That's a false statement. It doesn't matter what you plug into x or y, you're never going to satisfy the system of equations. That's because the graph of these two equations are parallel. Those lines are parallel, never intersecting. So there's no solution for that case. Okay. And then in the homework problem that you see, use either the substitution or elimination method. Does not matter which one. Those two methods are fine. Either one is fine, as long as you have a system of equations in two variables. Now, when you increase that to 3 or more variables, the substitution method and then the elimination method becomes much more cumbersome. So in the next video that we're going to look at, we're going to introduce a matrix, which is just an array of numbers. We're going to remove the variables and just be left with the numbers, making it much easier for us to solve these larger systems of equations.